Right. Our next presentation is demonstrating resilient and sustainable concrete benefits with slag cement from Shawn Kalyn from St. Mary's Cement. Shawn is a technical services engineer with St. Mary's Cement. He's been working with St. Mary's for more than 15 years. He received his degree in civil engineering from Ryerson University in Toronto, Ontario, Canada. His responsibilities include providing concrete solutions to the cement customers and promotion of concrete and cementitious products. Kalyn is involved with the PCA Sustainability Committee, the ICPI Technical and Education Committees, SCA's Great Lakes and Marketing Technical Committees, and is involved in the MIT Sustainability Hub as well. I would like to now welcome Shawn, and I will hand over the presentation slides to you.
Well, thanks everyone for attending, and would like to go over the use of slag cement when it comes to demonstrating resilience of concrete results with the use of slag cement. Our learning objectives today are going to be the key terms, definitions commonly used when discussing carbon impact of concrete, how the initiatives like Lead Point Systems, Architecture 2030, and Carbon Leadership Forum are influencing the use of our concrete materials, and how to select carbon impact of concrete using SCMs like slag cement and others. And also would like to talk about the specifics, and this is where we're going to go into mostly, is to include the use of EPDs and LCA Calculator tools that can show customers sustainable and durable options for concrete, not only from a short-term, but from a long-term aspect as well. So resilient concrete, durable yet mindful of long-term global environmental impact changes and challenges. According to the Resilience Design Institute, the intentional design of a building, landscape, communities, and regions in order to respond to natural or man-made disasters and disturbances, as well as long-term results from affecting of climate change. So one of the disclaimers, like we kind of were saying before on the disclaimers, there can be some short-term trade-offs and balances need to be determined for time of constructability and long-term durability and sustainability goals. So our example here, you can have two kids, these are my two kids, out in the middle of summertime. Obviously there's going to be a lot different protection than there is in the wintertime from protection. So in the spring and summer, we're doing sunscreen, and then in the wintertime, we're wearing more clothes and more blankets to make sure that concrete, in this case, would stay comfortable and be able to grow. Understanding the carbon impacts and the terms, there's operational carbon. That is a carbon load that is created from using from energy, heating, powering buildings, and so forth. And then embodied carbon is the embodied greenhouse gases that are emitted during the construction process of the buildings of making that material. And then carbon is a general term that's used for greenhouse gas emissions. It's not just CO2, but it can also contain methane and other equivalencies. Another term that you'll hear a lot of times is EPD, that is Environmental Product Declaration. This is a document that quantifies the information of life cycle of a product to enable comparisons between the same functional unit. We're going to get into that a little bit further on later on, but for the most part, one EPD cannot be compared to another EPD. One of the things that you do when you are creating EPDs are product category rules. The product category rules are the document that provides rules requiring the guidelines for developing an EPD. And then the life cycle assessment is what we're all trying to get to, which is to process, to evaluate, and improve the environmental burdens associated with the process, product, or activities identified, and quantifying energy and materials used and waste released into the environment. Here are some of the green building aspects that we are seeing, and a lot of people are familiar with this now. Energy Star, Green Globes, LEED or USGBC, Architecture 2030. We can see it's also into a lot of the codes and standards now as well, such as in ASHRAE, such as in the International Green Construction Code. So we are starting to see, as we keep on continuing, we're seeing a lot more standards and kind of rating systems that can help you lower your impacts. From the Architecture 2030, they had started, what they have is they wanted to see and show a reduction in CO2 emissions. So with the CO2 emissions, they all pledged, a lot of them, to try to be carbon neutral by 2030. And on this 2030, they were looking at the aspects of not just looking more at the building emissions and the greenhouse emissions created from the energy consumption of those buildings. So as you can see here, they were looking to try and get it reduced. Now you're starting to see a lot of people that are now going to not only just use that carbon reduction from the fuels that are being used, but also the carbon reduction from the materials themselves and how that is being used. That's the embodied carbon. And other things that we're starting to see that are popping up, and this has been coming on for about 4 or 5 years now, I believe, where you have cities now that have been pledging to reduce their carbon emissions. And in this case, you can see that in June of 2020, there were 22 cities that pledged to reduce their CO2 emissions from the buildings that are in that. With this, the City 2030 vision, we are making a global process in reducing our operating emissions, said Aaron McDad, Program Manager at Architecture 2030. According to the best scientific data and consensus, we have to phase out all fossil fuels by 2050. Why are we here? To reduce the environmental impacts of the buildings and the structures that we create. One of the other things that you're starting to see, and this just got launched in September 1st of 2020, is the Global Cement and Concrete Association has launched its ambition statement. The Global Cement and Concrete Association is made up of a bunch of members who obviously are cement producers and concrete manufacturers, and they have pledged to reduce the industry's CO2 emissions to neutral carbon by 2050 in concrete. Other things that we are starting to see as well, this will probably happen in the US Green Building Council as well, but on the Canadian Green Building Council, with working with the Treasury Board of Canada, which does procurement, they are looking at using low carbon cement, such as PLC, and also looking at lowering the carbon in the concrete itself. One of the things that we do see is we hear a lot of times that you hear people say, well, concrete creates a lot of CO2. Well, actually, yes, in a way, but no in another way. Concrete is also, next to oil, or more than oil and coal, is the most used product in the world next to water. So as we can see, this material that we are using has helped our society grow to what we are, and the ability to have the buildings, to have the transportation, to have all of that. So when we look at this graph that you're seeing here, this is a logarithmic graph. So with this logarithmic graph, you can see that concrete is way more used than asphalt, glass, brick, block, wood, natural fibers, man-made fibers, and carbon fibers. You can see how much there is. And the other materials, you'll see there's a lot of differences on that, even including steel. When we look at concrete and we look at it from the embodied CO2 energy and the amount of energy needed to create the concrete, we can see that from this, that concrete is actually a low carbon material compared to other materials. So if we're looking as we're going in having more issues with global warming, what materials are we going to look at using that have lower embodied energy and lower embodied CO2? As we can see from this, if we're going to move away from concrete, we've got to be very careful, because if we did that, we could be creating products that have more CO2 in those products, or creation of products that are going to generate more CO2. An example here is if you look at this graph here and we look at towards the timber section, we can see that yes, timber may sequester CO2 when the tree is living and growing. However, when we cut that tree down and only 50% of the material is used for timber, then all of a sudden we are seeing that we have higher impacts in regards to CO2 and embodied CO2 and the energy created that's needed to make that product. So how do we accomplish reducing our CO2? We use SMART. Do materials we need to use need to be new? Are there recycled materials or salvage materials that can be used instead of creating virgin materials? Building smart. Use materials, tools, and resources available to the buildings and determine the outcomes by using life cycle assessment. And then buying smart, using the environmental product declarations and LCA calculators to determine which products or how we add into those products give us the best solution that we're looking for. So when we look at it at first and we say, what is an EPD? There are several steps on the way to get to creating an EPD. First, you're going to have your product category rules. So depending on the product itself, we are going to use the ISO 2190, and that's the main building block for creating PCRs. And then you use that guideline, and then depending on the product you're using, you're going to basically use a guideline that's going to be connected to that one that's going to say how we create the rules for our current products. For example, right now, the Slag Cement Association is currently doing their PCR and are working right now with NSF to create the product category rules. Once that's done, they will be creating their second version of their industry EPD. So when we do an industry EPD or when we do any EPDs, what we're going to do is we're going to conduct an LCA survey, and we're going to look at all the life cycle impacts and do a life cycle inventory of all the materials that are used to create that product. Then the EPD is created. It's then can be third-party verified, and then after it's been third-party verified, it then gets checked and gets sent to be registered with a program operator. Some program operators are, for example, I just said NSF, ASTM is currently one, CSA, and a bunch of others. But basically what we're trying to get to and what it is on each of the products is going to be a nutrition label. Similar to like when we look at a bottle of pop or a bottle of Coke and you look at it, or you look at a package of food and you want to see what the nutritional value is or the amount of energy that's been used into it that you can get from it, the calories, it's going to show you. So we're doing a similar thing when it comes to the EPDs and nutrition labels for buildings and materials, is we're looking at the primary energy, the global warming, ozone depletion, acidification, eutrophication, and smog and other aspects. Here's a good example of, now we're going to look at an industry EPD, which would have been from the Slag Cement Association. Most of the EPDs that you're going to see on concrete are going to be on the what we call A1 to A3, which are going to be the raw material supply, transportation, and manufacturing. So this would also be considered as being cradle to gate ones. Ideally, what we're looking at from a building aspect is going from cradle to cradle, which means that the building gets built. After the building is being used, you're calculating and using all of that energy that it took to use the building, and then the destruction and recycling of that building. So we're looking at a full cycle to cycle loop at closed loop with what we're trying to do. But in this case here, we can see we have all the impacts, and you're going to see the global warming ones, so the category indicators, the energy, whether it was fossil or nuclear, solar, wind, biomass, geothermals. You also will see the material consumption, non-renewable materials, renewable, recovered, and fresh water. And then we'll see waste generated, whether it's hazardous or not hazardous. And then as we see, as these product category rules, like I talked about before, those typically are done every 5 years. And then you may see some more indicators or less indicators come in as the sustainability aspects in EPDs continue to evolve. So how does slag cement fit into the picture? And how does slag reduce the carbon footprint of concrete? What are the valuable benefits of slag cement contribution to concrete? And how do I use an LCI tool to convey these benefits? And how can slag cement be used to get LEED credit? Well, here's an example of the Portland Cement EPD, and the Portland cement industry is currently right now going to be looking at their second version of their industry EPD. They're currently did the product category rules, and they are now right now collecting all the data and having that. So by next year, most likely in February, there will be an industry EPDs for Portland cement when it comes to Portland cement. Also for the PLC cement, there will be one, as well as for masonry and stucco cements. So when we look at this industry EPD that they did from the last time in 2016, we can see that the global warming potential was about 1,000 kgs of CO2 equivalent per metric ton of cement. Now, when we look at the same thing with slag cement using the slag cement industry EPD, we can see that the global warming potential is 150, well, technically 146 kgs per 1 metric ton of cement. So we can see that there's a drastic reduction in CO2 emissions that would be a cause from that. So with that, the more slag we put into it, we're directly impacting the amount of Portland CO2 getting reduced from that. Here's another way, which is kind of like what Jason Weiss was talking about before, was when we look at using PLCs, we're going to see a reduction in the environmental benefits or increase in environmental benefits of using it, because we can see a reduction in the global warming potential. So in this case, when we look at the cement industry one of Canada, when they did it in 2016, when they compared type 1, or in this case you see GU, which is what we in the US would call type 1, and PLC or 1L in the US would be GUL in Canada, we can see that there is basically a 10% reduction in the CO2 emissions from using PLC versus using type 1. When we go and we look at it in graphs, and we're looking at it from construction and the energy consumption, we can see that the global warming potential of OPC in this case is 1 ton per 1 ton. We look at the PLC, we're down to 0.9, and as we saw before with the slag, we have a reduction there. We also see a lot of energy consumption or energy reductions being used as well, because as we can see, when we're using the ordinary Portland cement, there's the energy is about 6.5, and then PLC, we've got a reduction there. And then with the slag cement, we have a lot larger reduction there, because most of the energy inputs and impacts for slag cement is when we have the creation of the blast furnace slag being created to make steel. LCA results we also will see when we look at different concrete mixes. We did 100% Portland mix. We're going to see that we're about 256. When we went to the US average, was about 244. Now this was done on the original NRMCA's EPD, so they are now actually into their 3rd iteration of the industry EPD. But as we can see, as we're using slag into that and increasing the amount of slag, we will actually see lower numbers. One of the other things that's also the good impact on it too is non-renewable resource use. So because we're using slag, and slag is a recovered material, we're going to see that we're not using virgin materials as much, and you'll see that same reduction in numbers. Primary energy consumption, you'll also see that that information is also showing lower numbers. So if we were to use this case, as all these numbers you're seeing were done on a 3,000 PSI mix. So the possible savings would have been 100 kgs of CO2 reduction, 200 kgs of resources, and 500 megajoules of energy not used. So when we look at a study that was also done by CTL, this is a good example that not only in ReadyMix, but in precast as well as in block, we can see reductions by using slag for the environmental impacts. So in this case, if we look at a ReadyMix, typical 3,000 PSI is about 376 pounds per cubic yard. For a ReadyMix of 5,000, it's typically about 564, 611 in that range. And then with precast, a lot of times they could be up at the 850 pounds. Block, in this example, they had 337. So as we can see, you can see the volumes and the amount of aggregates and the fines in the course, as well as the amount of water that may have been needed to make the products. So when we look at those different ones, we can see that if they use 35 or 50% slag, you're seeing a great diminish in the amount of CO2 that is in those actual products. So as we can see, by going and using slag cement, we're reducing those numbers. Now we're going to get into some realities. This chart that you're seeing here actually comes from the LCA Slag calculator that we will be discussing a little bit later on. And in this case, this is an ODOT example. So ODOT in 2012 had gone from being prescriptive-based to performance-based. And when they went to performance-based, it was not for environmental reasons, but more for the impacts of reducing the permeability in their concrete. So reducing the permeability in concrete, they started to require the uses of slags and fly ashes and other SCMs. And in this case, we can see that we took a bunch of different mixes. QC1 I'm showing here is a 600-pound cement mix with 25% slag replacement. Then the QC1-2 with 30% replacement, and then one with 25% slag and 25% ash into it, you going to a 50% replacement. And then compared it against the original Class C, which the Class C originally was 100% straight Portland cement. And then looked at Class C option 1, which was the 600 pounds of cement with a water reducer. And then the Class C option 2 was a 550 pounds of cement with fly ash. And then the option 3 was 550 pounds of cement with slag. So the fly ash, I believe, was at 15%. The slag was at 30%. So when we look at the Class C concrete, we can see that compared to the NRMCA industry benchmark. Now this NRMCA industry benchmark, this calculator that we're looking at or will be looking at was based on their second iteration of their EPD. And in that EPD benchmark, we could see that if we would have had a Class C concrete from originally, we would be 15% higher than the NRMCA's benchmark. And we will see it as the NRMCA, as well as other industries, we will start to see that as they continue to keep doing these benchmarks and doing the industry EPDs, we should start to see lower reductions in CO2 emissions and other emissions. When we look at the benchmark 4,000 PSI mix, that benchmark is basically showing 511 pounds of cement for 4,000 PSI, 18% slag, 88% ash. Now, these mixes were basically taking the average of what is used throughout the country as a whole and using that fictitious PSI to make out what that would be. So it has a CO2 content of 281 CO2 per cubic yard. When we look now at the ODOT changes and we look at what they now did for the performance side of it, and we look at it from the environmental side of it, we see that just from using that 600 pounds and taking out 150 pounds and now putting in that as slag, we now see a reduction that's 7% less than the industry benchmarks and 19% less than ordinary Portland cement if it would have been used in that application. So kind of, as we can see here, there's a lot of environmental benefits as well as durability aspects that slag can achieve. Here's an example now of low carbon concrete using slag cement. So in this scenario, we're going to use a ReadyMix producer, a concrete flatwork construction company, and they need to find ways to lower their global warming potential on a residential or a retail shell and core box store that's going to be built. And this is fictitiously put in Avon, Ohio. So in this case, the project consists of the following concrete items. There's a 3,000 PSI for the concrete footing, and then there's a 4,000 PSI for the interior slab on grade. Now, the designer of this project, as they're trying to reduce their global warming potential, has actually put limits of the amount, being prescriptive, the amount of cement that could be used for the project, or they could go and use a global warming potential number per cubic meter. So in this case, we can see the 3,000 PSI. They're saying that the maximum Portland cement you could use would be 456, or you could use a global warming potential of 313 Ks. Then for the 4,000, 503 or 338. So in this case, this could be restricting the product and the way that the contractor could be able to do it. He might be all right with that 3,000 footer, but he could have some issues when he's trying to do the finishability on that 4,000 interior slab on grade. So as we can see with these numbers, we got to watch on how we're doing it. So a better way of doing that is actually to now use the resources and to look at using the Slag Cement Association's information in their tool stuff. So if we look at the EPD, that's a good example to see, okay, how does slag compare to a Portland cement for reductions? So we could use that. Then the next thing we could do, which is even better, is we can actually now, instead of just trying to use the charts of the EPDs, we can actually go and use a calculator that actually already intakes and collects the information that was done from the NRMCA's second version of their EPD, as well as the Portland Cement's information, as well as the Slag Cement's information, all in one convenient tool that now allows us to be able to calculate what the CO2 content would be and the other parameters for a given concrete mix. So here was that owner's requirements. And as you can see here, you can see some of this is starting to occur. This actual sheet that you're seeing here is actually for a city, and I believe it's in Oregon, the state of Oregon, that's looking to do this information. Now, when we limit the amount of cement, Portland cement that could be in a mix, we can't just go and generically go and say this, because depending on the project, depending on the application of the concrete, for example, if it's precast, it may have high Portland cement amounts initially, but because of the ability to make it thinner and so forth, you're going to see that if we just use these numbers, it's not going to work out for everything as a whole. And in some cases, we may be able to reduce the amount of cement or increase the amount of cement depending on the volumes of what we're looking at or the application that's going on. So that's why it's better to use a calculator and compare it to the industry benchmark information to try to reduce these numbers. Using the LCA SCA calculator, what we're going to show and go through this right now is kind of show you the customer tab, which is going to see where you enter the mixes, the type of IDs, the class strengths you're looking to do, and the type and mix proportions that you're looking to use and add into it. So basically in this, we're going to see that we're going to put in our mix ID, and in this case, we're going to say it's a footer, 3,000 PSI max. So in this document, we're going to see, we're trying to compare the differences between using the specification that they required of maximum 456 pounds of cement, or we're now going to start looking to use slag. So in this case here, we've done an example where for a footer, it was 456. And then we see for the footing with slag, we used 350 pounds of cement, but 120 of slag. So we're going to be higher than the actual total cementitious that they had in there, or for the Portland. So we can see that we're going to get a little bit more workability out of it. Now, if we went to 4,000 PSI footer or 3,000 PSI footer with 40% slag, we can see that we're going to make it a little bit maybe creamier and so forth. But we got to watch, depending on the amounts of the volumes we use, that as we increase the amount of slag, if we don't have heat to generate the initial strength gain, then we may need to watch the amount we use so that you can still get the constructability that you're looking to do. Then we're going to look at the other two parts, which was that 4,000 for the flat work. And we can see that we're using, in this case, the maximum Portland cement, which was 503. But if we're looking to use it with 25%, we're going to see now that we're at a 540 in this example. So in this case, with this calculator, you're going to see that there are different regions. So depending on the region of where you're at, and that's why it's very difficult to compare EPDs to EPDs, because a lot of the times you're going to have to need to know what the transportation is. You're going to need to know what the energy grid is. And you're going to need to know what the kind of typical materials are that you have in that area. So the materials, for example, limestone that could be in Michigan is going to be a lot harder and a lot different than the limestone that you're going to see in Florida. So those are going to impact the way the concrete works and the way the ability and to be able to make the concrete that you're looking to make. So in this case, we're going to use the Great Lakes as the Midwest as the region. So that's going to have the power grid that's being used there. And in this case, we're looking for the maximum this that you're going to see here is a slag substitution chart. The reason why we're onto this one is that's where I can do that slag region connection. So using the SCA calculator, the comparison benchmark tab will show the environmental impacts. And now when we look at those same mixes that we did before, you're going to see at this 100%, that 100% is always going to be the PSI benchmark number. So for the first 3 mixes, it's going to be the 3,000 PSI. For the next 2 mixes, you're going to be at the 4,000 PSI. So as we can see here, that if we just did it with the straight Portland, we're going to be higher than the industry average. But if we're using it with that 25% slag, we're going to see that we're lower than the industry average. So using the SCA calculator in review, you go to the slag substitution calculator and you just want to look at it quickly on a certain mix that you're looking to use, you can use this bar to lower and raise the amount that you have that you're looking to use. And then you can just select the mixes. Now you're going to see that this mix that you're going to see, the second section one, is going to be the information that you had put in that current custom mix sheet. Now we're going to go into a little bit onto lead and going through some of the aspects of the old version of lead versus the new version of lead. We knew that under the lead rating system before, a lot of the credits were single attribute credits. So for example, if you had an FSC wood, you got a point. If you had recycled content in there, you got a point. If it was a regional material, you got a point. Well, now what they've done with the new versions is they're now trying to go towards the EPDs and sourcing of materials and material ingredients. And by doing this, they're looking at it from a holistic approach versus looking at one ingredient versus another ingredient. So one of the things that is always a key to watch when you're looking at using the lead documentation, and I get this all the time, is people go and think that, okay, if we're using concrete, I need to get the cost of the material from the concrete producer, which that is not the case. What you're going to see, and this is written right in the lead documentation, that says the product and material costs include all taxes, expenses to deliver the material to the project site incurred by the contractor, by excluding any costs of labor and equipment required for installation after the material is delivered to the job site. As we know, for example, with ReadyMix concrete, the concrete is made at a plant, then delivered to the site, which then the contractor gets it. So there's going to be a difference between the cost of it being made on the site. It still has to be transported to the job site and so forth. So that's why the calculation of these costs should be calculated by the contractor or the project designer. One of the things that the project designer could do is, if the contractor doesn't have the actual material costs broke down in his bid, they can use the material actual costs, or they can use a default material cost. Default material cost is the total cost of the materials, and it is calculated to assuming that 45% of the total construction cost is the material itself. So when we look at the material requisites, here's some of the credits that are there now under the materials resources section. You got building life cycle impact reduction. We've got building product disclosures and optimizations. We've got sourcing of raw materials. We have material ingredients and construction and demolition waste management. So here is one of the credits that we were kind of talking about before when we're talking about EPDs and how does that work for into lead. One of the things that they're looking for in their option 1. So under the materials credits, you're going to see building products disclosure and optimization. Option 1 is going to be having an EPD declaration. So if you have an EPD and what they want is at least 20 different permanently installed products sourced from at least 5 different manufacturers. So for example, if you have a concrete that's going on there, and you might have one concrete manufacturer putting in, let's say, footings, walls, and they could be putting in a floor slabs as well as putting in a grout mix. There could be 4 or 5 different materials that could be used. Each one of them could use the exact same EPD information and use that depending on what the mix design was used on it. So in this case, we're going to see that product-specific declarations, if you have one, but it's not third-party vetted, then it's worth 1/4 of a point. If you have one that's an industry-wide one, it's worth 1/2 a point. And if you have a product-specific verified type 3 EPD, then it would be worth 1 full point. And now what also changed though is when they went to the version 4.1 for LEED v4, they reduced the impacts of that. So it used to be 20 permanent products. It's now down to 10 EPDs required. And the industry EPDs went from 1/2 point now to a full point. And then the whole product third-party EPD one has now gone to 1.5 points. So they try to make it a little bit easier to get if you're looking to do the 4.1. And also just to let you know that with the 4.1, if you're using the version 4, you can add in the credits of 4.1 and use it from that standpoint. Another tool that or another point that they have under LEED, under the building product disclosure, is the option 2. And the option 2 is use products that comply with the criteria of 50% below the cost of permanently installed products. And in this case here, they're looking at, when we looked at that LCA tool, what ones are showing the reductions in these impacts. So for example, global warming, ozone depletion, acidification, they want to see that you have at least lower than the industry average. And I'll get into that in a second. One thing that we're also looking at in this is that tool or that credit itself. When we look at the actual point numbers of it, if you get a 5% global reduction compared to the industry one, you're going to see they can get 1 point. If it's 10% reduction in global warming potential, then you can get up to 150% or 1.5 points. And then if there's a 20% reduction, 200% or 2 points. So now we're going to go back and we're going to look at using that LCA calculator again. And in this case, we're looking at a 3,000 footer, a 4,000 interior wall, there's 4,000 exterior concrete, a pan stair mix, a 4,500 air and train concrete for exterior concrete, as well as there's a mud mat that's a 1,500 lean. And then there's some lightweight for some lightweight floor concrete that's being put in. So in this case here, if we look at the first mix, which is that 3,000 footer, looking at that credit, we can see that we're below the industry benchmark. So therefore they would be able to get points for that first mix, that second mix, which is a slab on grade, as well as the interior floor, they'd be able to get reductions. And then in this case here, when you're seeing the 4,000 air, this mix here had a straight Portland mix. So in this case, it was higher than the industry average. So therefore, we wouldn't be able to use this. However, what we can do is we can go in with that designer and say, as a ReadyMix producer or as a contractor or a concrete manufacturer, to go in and say, we can reduce our emissions on this if you allow us in the specification to start using items such as slag and that, and show that reduction in those numbers and be able to work on changing that. And then we can see when we're using that 4,000, 4,500 with air, in this case here, it was a mix with 30% slag, and we can see that we reduced it compared to the industry average. So when we look at this, there's also another aspect to this, which is whole life building aspects. So LEED isn't just looking at it from the industry or the embodied carbon of the concrete, but looking at the embodied carbon of the material, but looking at it from the holistic of the whole building itself. So in that case, they have another credit for that, which is they want to reduce at least 3 of the impact reductions, such as global warming, ozone depletion, acidification or eutrophication, or formation of ozone and depletion of non-renewable energy resources. So if you have 3 of those categories in that building, then you can show the reductions. In that reduction, you're going to see that they're going to give you, just for putting it in the enclosure, 1 point. If you get a 5% reduction, it's 2%. If there's a 10% reduction in the whole building impacts, then you're going to see 3 points. And then you're going to see 20% reduction and the same amount for the reuse, you're going to get 4 points. So when we look at that same LCA calculator, there was another tab on there where you're able to put in the mixes that you had for the whole project and put in, or you'll see up at the top here where it says that 3,000 footer, the slab on grade, that in 4,000 interior of the air. You put in the amount of yards that are going to be in that. This is going to assume that the building was a 50,000 square foot building, 5-story office building that typically would use 2,800 cubic yards of concrete. So this calculator is going to see what those impacts would be. And as you can see with this, we're going to see for the whole building, for the concrete aspects of it, that from a global warming or climate change, we're going to see that we've got about a 10% reduction. On ozone depletion, we're almost getting about a 35% reduction. Acidification, we're seeing another 10% reduction. So this is going to help you with those credits. So we see here on that credit, we have at least 3 of these impacts are shown here as being reduced. Now, one of the credits that are still in there from the old time was the building product disclosure and optimization sourcing of raw materials. So in that, there's actually a new credit, but this has gotten removed off of the 4.1, but it's still in the original version of 4, is if you have a corporate sustainability report, then that corporate sustainability report would be worth a full point. If you have a self-declared report, then you would get 1/2 that point. So if you have a global reporting initiative sustainability report, that works. The Organization for Economic Cooperation Development guidelines, if you have that, a UN compact one, or an ISO 2600, or the USGBC approved program, then you would be able to use this credit. One of the other things that they also have, which was in the existing one from before in version 3s and in version 2, was the material reuse, recycled content have now been combined into one area, so that you could still get a credit for that, and extended producer responsibility could also be in that credit. So the recycled content is still there. The regional content, however, has been changed. A lot of those credits that we saw before, if the concrete is within 100 miles, meaning extracted, produced, manufactured, and delivered to the job site within 100 miles of that project, where 90% of the components in that concrete are within that 100 miles, then you can get the extra credit for those points. Now, when we look at what we've looked at today, we're going to see that environmental impact declarations are feeding the whole building life cycle assessment. So that's going to give us the embodied portion of it, obviously with concrete and any type of building product, where you also have a lot of good attributes that can occur in the building cycle or the life cycle portion of the building, meaning the use phase of that building, where we can see a lot of the good environmental impacts of using concrete. For example, a lot of concrete buildings will last for more than 100 years. So if they last for more than 100 years, we're not having to replace and bring them and reconstruct them all the time, which is going to save a lot when it comes to the environmental impacts of that. So environmental product declarations can give us more specific carbon footprint information. However, they can be difficult to compare one EPD directly to another one. The other things that we can look at is whole life building aspects and look at multiple impacts of the building material over the entire life cycle of the structure. This takes the information from the EPDs and calculates a better holistic picture of the true impacts of the construction and the use and the waste reuse of that project as well. One thing I didn't mention is one thing we are looking at and we are starting to see is when it comes to concrete, that the concrete itself absorbs CO2. So depending on how we do these buildings and how we leave the surfaces of the buildings, or even in the construction or demolition phase, we can crush that concrete up to give us more of a surface area, which now that concrete actually absorbs CO2. So similar to like what wood would do with the tree, where the tree grows and then absorbs CO2, concrete is actually a building material that after it is first going through the hydraulic process, it actually then starts to reabsorb CO2 back into it over its lifespan. Also, one thing they wanted to mention too was there is specialty software to help develop for us to design and for construction professionals to use to figure out the whole impacts of buildings. One example is the Athena Impact Estimator, and then there's another one called Tally. With that, that comes to the end. And just wondering if anyone has any questions. Oh, one last thing. When it comes to cement and concrete specific LCAs, we can use the ReadyMix concrete lifecycle assessment calculator that it can be free to be downloaded from the Slag Cement Association website. The calculator lets the designers to custom mix designs and then substitute various amounts of slag through a simple dashboard interface, allowing them to compare different mixes. The tool also allows the input of mix design information to a hypothetical whole building life cycle scenario so that the designer can kind of give an idea of using different concretes and different materials in there and how that impact is going to impact the holistic of the building itself. And there's also step-by-step instructions available on the website that allow you to help you work through using that tool. With that, is there any questions?
Thank you, Shawn. That was a great presentation. And there will be a quick demonstration at 2:30 today on the LCA calculator, just quickly going through where to find it, how to download it, and then walking through each of those, the tabs in the calculator. So we'll be doing that again at 2:30 today. Looking over the questions here really quickly. One question, please elaborate on the global warming potential numbers given for slag cement. Is that a mixture of Portland cement and slag or just the slag? And then there's a second part to that question, but I'll let you answer that first.
On the, I believe what he's asking is on the industry benchmark one, that industry benchmark is just the manufacturing of slag cement. So that's the manufacturing from when the granules are created from the slag runner to bring in that product to the granulate, at the granulator, the creation and the energy and the inputs of creating that, the waste resources of that, as well as the drying of the granules and then the grinding of the granules, then put into the terminal where it can now be used as a cementitious product. That's what that EPD or the carbon footprint was for.
Okay. And I think you kind of already touched on this, but the second half of that question, and if you were to consider the embodied carbon of slag material only, would you consider a global warming potential for it, or would you consider it as a byproduct of another industry and thus emit the embodied carbon when used in concrete?
Yeah, because slag is made from the steel process, when you're making steel or iron blast furnace slag, what it is you have the iron ore is melted along with limestone, which has silica in it. So what happens is the iron ore, the iron portion floats to the top or stays down on the bottom, and the slag, which is now going to be silica, limestone, alumina, that all comes to the top. That is where the process would then stop. What used to happen was on the steel side of it, they would just go and dump that and now make it as an aggregate or just leave it or stockpile it. What we do is when it's in that hot runner going to be, which would have just went to a stockpile, we now have it as a going to the granulator. So that's why you're going to see a reduction in the amount of energy inputs, because it's recovered material.
All right, that was the last of the questions. Does anybody else have any other questions they'd like to add in? Oh, one of the figures showed a quote US average mix. Is what that person was referring to.
Yeah, the US average mix that you're seeing there is going to be when they created the NRMCA industry EPD, when they looked at the mix design. So if they would have taken a 4,000 PSI mix, what they call the US industry average mix is for that 4,000 PSI category, or that 3,000 PSI category, or that, let's say, 7,000 PSI category, they had taken a bunch of mix designs that would have typically been for that 4,000 range from all over the country, and then used those mixes and average them into one. That's what the US average mix is. That's why you'll see that they would have taken, for example, if you had it in California, you might be using gravel, where the mix that was used in the Great Lakes region, such as Michigan, could be using limestone. So when you look at the industry average mix, it's going to take into part all of those and then average that out. So that's why there would have been a little bit of limestone, a little bit of crushed gravel. There also, when you look at it from the cementitious side, you're seeing that there's slag, Portland, fly ash, silica fume, all those would have been in there.
Right. One more question just came in. Are you seeing more specifications coming out like the example you showed based on the concrete's global warming potential?
Yes, we are seeing a bunch of them starting to show up, and that happening now. The issue is a lot of times people are meaning to do it on the nice side and trying to do it well. Unfortunately, though, they may not know the impacts of how that can impact them.
And what was the OPC replacement level on the US average concrete mix design?
The OPC level on the US concrete mix design, I have to go back and look at it. It depends on what the grade level was, whether it was a 3,000 or 4,000 PSI mix.
Okay, and we can certainly provide any follow-up questions people have between myself and Shawn. We can get you answers that you might have beyond what we were able to cover in today's presentation. Feel free to visit slagcement.org for more information on this and to download the LCA calculator that's available. And there you will find our contact information as well, should you have any other further questions on this.